The next topic is the CAN. It's basically a protocol used in the automobile industry, basically. That is for the communication between various ECUs present inside the automobile electronic components. All right. So the full form stand for this is the controller area network. All right. So this was originally built, or it was I originally this protocol was introduced by Robert Bosch in 1986. Okay, it's a older uh, uh, protocol. If you look at that, it is in the industry since 35 years, but still nobody could replace that. Only some upgradations have been done, right? Only that's the thing, right? But none of the other uh, automobile manufacturers or any component manufacturers have could replace this. So it's like it's so good. Okay, using only two wires, you can connect any device, any electronic component that is present inside an automobile. Okay, so uh, that's the actual very basic feature about this CAN. All right, it's a network, and there is a protocol to be followed to communicate. Okay, so what is a very fundamental idea about the CAN? It's just like this. It is a asynchronous serial communication protocol. It's a communication protocol. So you see, the word asynchronous means there is no common clock signal shared between the transmitters and the receivers. Okay, if you have the clock to control them, we call it as asynchronous. Again, that's the first feature, asynchronous, and the second feature, you can see that it is serial communication. In the sense, bit will be sent one after the other. Okay, now in this CAN protocol, the message, you are trying to uh, make some rules to control the messages. Okay, and again, you will not worry about the address based transmission of the data, right? Always it is a receiver's choice to receive the data or not. Okay, so you see that normally I send an address and then I'll actually send the specific message corresponding to that address. That's not going to happen here. It's a slightly different version of the communication protocol where not based on address, you send the data, and the devices who wants to receive, right, because many devices will be connected to the CAN bus, right? It depends, right? Whether I should read this data which is coming or not will be decided by the receiver. Okay, so I'll write another feature over here, the one which I just mentioned. It is basically it's a message based protocol. Whereas if you look at the previous one, that is I2C, that is address based. Okay, so I'll write it is not address based. Okay, so previously there is a before sending the message, the controller will send the address. Whoever has that address has to respond. Right? So normally you see now that actually may take some time of your overall whatever duration is required. Right? It takes up some time. So now you don't have to worry. Simply send the message. Message itself contains whom it is supposed to receive, right? And the receiver will decide whether to receive or not. Okay, right. No, again, we have two wires. One is called as the CAN H. Maybe we can consider this as a high, and another one the CAN low L. So normally this is a two-wire system. That is, if you look at the automotive's actual communication bus using the CAN, you will see that there is a twisted wire system. Two wires in the twisted fashion. Okay, twisted wires. We call twisted wires. Right. Now again, one of the very commonly used termination resistance is 120 ohms. Okay, 120 ohm termination. This is something like the matching, okay, impedance matching concept, right? So, okay, let me draw a diagram to represent this, right? So, uh, let's write few blocks here. So this is the first uh, node of CAN. There is a second node of CAN, and let's say these are the devices. Can be the ECUs present, right, in our system. Now we will use two wires for the communication purpose. So this is say CAN H, and I have another CAN L, right? So here we will be introducing a resistance. That's a termination resistance, right? So I'll write RT. It's 120 ohm anyway. It's just now we have written that it's the same one. Okay. So on the other side also, everywhere we'll put the same thing. So on this side also we are going to have. So there is another RT, right? Okay. Now the connections will be, right, will be connecting one to the lower line, and we'll be connecting one more to the H line. Okay, same thing repeats for all the devices. So you see how many devices we want, we can connect, right? We just have to have two ports. Like this. So again, this is just a representation purpose. I'm writing three. There is fundamentally there is no restriction saying that how many devices you can connect. Okay, now let me write that this is a CAN node 1, node 2, node 3, right? So the high line is CAN H, and this is CAN L, right? So this is the general architecture, right, which we use for the CAN communication protocol to be implemented. Okay, right? So where do you see the applications? Majority of the application in the automobile. So I'll just write, first we'll write the applications, right? The first one is the uh, basic transportation systems, and it includes automotives as well. Okay, right? All the automobiles. In addition to that, we'll use even in the marine systems, railways, the aircraft, everywhere the same thing is used. Okay, then you will also use in the uh, home automation, and even in the buildings like the elevators, right, etc. Right, where there also we will be using the same thing. Okay, then the agricultural equipments, huge construction machines, etc. They are also going to use. So I'll just use home automation and construction. Okay, so everywhere, anywhere we see some automobile related this, it's being used. Okay, right. So those are the major applications which we are using. Now we'll see why do you need this, right? What was the requirement at first? So because before the CAN was implemented for the first time, there were many other protocols. Why, right? This particular uh, protocol was required for the first time. So that's the need. Need for CAN. Can you guess? So we want to build the message oriented protocol rather than the device oriented, which means, right, I have to reshape the architecture of the network, right? So if you see, right, the general or the conventional uh, network, right, then most of the time this is how it's going to look like. I'll write the conventional network. So how the conventional network looks like, it will be something like this. Let's assume. So I have, so every block is one ECU, right? If at all I'm not using uh, the CAN protocol, then I will be connecting the devices in maybe this fashion. Okay. Okay. So let's see that. This is a conventional way. So I have, let's say, assume I have a old car which has no idea about what is CAN, and right, we wanted to connect multiple ECUs. Okay, so ECU one, maybe this is coming from the this unit is the odometer part. Okay, then there is another fuel gauge related that is ECU two. Okay, then there is a microprocessor or a microcontroller, or mostly it is a onboard CPU, right? So that is ECU 3. I may have something related to the music system, that is ECU 4, and maybe something else, maybe the ADAS system or airbag related something, some ECU which controls that. Okay, so this is ECU 5. Okay, so if at all we are not using the CAN, then mostly the connections will be something like this, let's assume. Okay, so this could be the possible connection between the ECUs, right? So some require a single line connection, some devices require two wire connection system like this, maybe, right? And some may require three or more wires as well. So you see, I'll try to implement every problem that is associated. So this connection is a two wire. Again, I may have let me say another one, so that is something like this. It's a one wire system. All right, then I may have, okay, so let me assume that this ECU 4 to ECU 5 is, say, three wire system. Okay, you see that, right? Every device communicates to other device in a different fashion. There are multiple protocols required, right? One wire system is a different protocol, two wire systems is a different, right? So you can see that, right? It's actually pretty complicated, right? Designing this kind of communication system inside a very small space, like the whole car is, you can see that the communication will happen less than 4 meters of space, correct? So within that, implementing so many types of protocols become pretty difficult. It's actually a very tedious job, right? So they wanted to overcome this issue, right, by using, by that's why they required a new protocol wherein you use a common number of wires. Okay, and you try to fix the number of wires, and every device has to communicate through the common bus, and right, following the common set of rules, right? So if at all you can, so we may ask that, okay, two wire system already exists, that's for, say, I2C, right? Why don't you use that? Possible, right? So now the answer is that it was something like, you if you remember, I2C was used between the various components inside a chip. Okay, it's like I have a, so consider the example we uh, we considered earlier, like I had a 8051, it's a chip. Okay, I had a EEPROM, that's also a chip. That's all. You between the chips, yes, this is fine. Okay, but now you see, it's not a chip when it comes to the ECUs, right? They are the controlling units of various components of a vehicle. Right. So their maybe the power of operations, their bit representation, everything might be different. Okay, it's not the common one which we used like earlier. Okay, everything uses 8 bits only, you can directly implement. That's what we had discussed, right, in case of a I2C, right? So the differences, right? This requirement itself is completely different when it comes to the CAM. The requirement is slightly different. So again, one more thing related to the requirement of CAN was every year, the automobile manufacturers will bring a upgraded version of the same vehicle, correct? Adding new components. So in this conventional network, you see, I'm going to add a new thing to my car. Okay, maybe I want to upgrade some lighting system to LED, upgrade something. So that controller ECU6, if you want to communicate with this, I have to add 2 lines. With this, I have to add 1 line. With this, I need to add 3 lines. Very difficult, correct? The new system addition of a new component is also going to be a tedious work. So upgradation is going to be very difficult. So you see, you understand the problem, right? So for that reason, if you make a common protocol that my new ECU6 will also follow the same thing, then no issue, right? So addition of your new component to the above said system, right? You see, this one is very easy, right? Bring a block, connect it to 2 wires, that's all, correct? So that's the problem. So that was the need of what is called as a new protocol, and the protocol implemented by Bosch is the CAN protocol. So now I come to the technical features. So earlier what I told, right, that was not a technical feature. I just told that there are 2 wires, right, etc., high, low, etc. That's not the that's a physical feature. Now I am going for the technical feature. This is the actual features of CAN protocol. So the first feature they implemented is called as the flexibility. By this time, you already know what is the flexibility, right? All nodes are connected, right, on 2 wires. That 2 wires, the Bosch calls it as a differential cable. Okay, so all nodes get connected to differential cables, right? And it means differential cable has a specific feature that also I have shown you in the diagram. It is terminated with the fixed value of a resistor. Okay, now you see why it is called flexible, because any node can be connected or disconnected without disturbing other nodes of the network. You don't have to change anything. It's like a, so whenever you see that if I want to implement or if I want to add a new device to the vehicle, right? Newly bought vehicle, you don't have to cut any wires, just right, just plug in, right? Because there is a CAN. Nowadays, CAN is implemented in almost every vehicles, right? So you don't have to cut any wires, simply, right, do a plug in. Okay, so the first feature, flexibility, comes because of this. So that is any new node, right? I'll write any node can be connected or disconnected. Connected or disconnected without disturbing network. Fine. Okay. Next, this also I have mentioned, but I'm going to elaborate that now. So the second feature is that the CAN is message based. CAN is message based protocol. So any node can broadcast a message on a CAN bus, and all other nodes will be able to listen to that broadcast. Okay, including the transmitter, right? Whoever is sending, they will also listen to what has been sent. Okay, but receiver will have a choice to receive the message or, okay. So if at all, it's address based protocol, like the peer-to-peer, point-to-point communication was happening in case of a message address-based protocol, right? So here I'll write unlike the address-based peer-to-peer communication, that it actually, this sentence gives you the complete idea about what is address based. Address based is from a transmitter only to the receiver. Nobody else will be able to catch that. Okay, so unlike that, in CAN, any node can uh, broadcast the message on the two wires which we have considered, right? It is called the two wires all together called as the CAN bus. Okay, on the CAN bus. And when somebody sends a message, uh, all other nodes, each and every node can listen to the broadcasted message. Right. Everybody will listen to that, and right, taking the message or not receiving the message, right, is dependent on the message itself, right? Whether you want to receive or not, it's a receiver's choice. Okay, so now it's very clear that the one of the advantage being here is that you send a message. Let me assume that I want to send common message to 5 different devices present on the bus, right? You see the advantage, only one message, no 5 messages. Same message is sent addressing different devices. Different devices will be able to receive that message at a given point of time, correct? Maybe it's something like maybe you are designing a automatic car. Fine, it has to decide a lot of things, but the main computer wants to apply brakes, decide, right, looking at certain conditions, right? So maybe simultaneously with the brake something else has to be, right, given the same message. You see that, right? The controller can put the message, right, some message to, it can put the message on the CAN bus so that both the devices will receive that message simultaneously. Okay, that's possible here. Otherwise, if at all not going for CAN, you need to send 2 different messages, maybe of 2 different sizes. One uses 1 bit communication, one uses parallel communication, 8 bits. So it has to decide what message I need to generate. Okay, so that the the braking system understands that. At the same time, there is another device, right, which means you have to send a completely different message, right? So that problem is, right, eliminated here automatically, because every device that you have connected is can listen to the messages that is coming on this bus simultaneously. So that is our next point. It is called as the CAN is a multi master communication. Okay, so write that CAN is multi master communication. Right now you see, any node can transmit or receive any time. That means, right, who can drive the CAN bus? Anyone can drive, any device connected to the CAN, right, CAN bus, they can drive the CAN, or they can start the communication, right? So any device connected to the CAN bus can uh, drive the CAN bus, okay, and start the communication. So what is the advantage of this? It the CAN, compared to any other protocol used in the industry, it has the highest adaptive feature. Okay, right? Maybe right. You can actually connect any number of devices. You can remove any number of devices. Every device can communicate with each other, right, etc. So that's one of the very basic requirement in the ECU part. Whenever you go to the ECU design, right, we may have to study that in a different subject, but ECU design is very important. That requires a lot of safety features to be included. Okay, what is the power calculation, how much current, etc. Many things are there to design, right? So this particular protocol enables you to connect any ECU to any other ECU. Very good, right? So that's why this is a very important feature. So fundamentally, this is a multi-master communication system. There is no single master. You have every device that is connected to the CAN bus is a master. Okay, it can start a communication provided it satisfies the protocol. Okay, then as we know, we are looking for message prioritization. So right, the CAN offers what is called as the message priority or prioritization. In a vehicle, many ECUs are they're they're connected. Each device has its own what you call safety features, right? uh, and they are pretty critical as well. Okay, the messages would be processed at a higher priority whoever has some safety issues. Okay, now the CAN protocol actually assigns some identifier values to each of the messages. Okay, so that right, whoever is manufacturing or whoever is implementing or whoever is connecting a device to the CAN bus can decide the message priority by assigning a lower or a higher identifier value of the priority. Okay, so let me write in this way. Uh, okay, during the implementation, maybe the manufacturer, because there has to be some freedom to the manufacturer. They cannot the original like whoever is building the CAN bus, they cannot say that okay, device connecting to my first position has highest priority. No, it cannot be like that. Okay, so there has to be a freedom saying that okay, any device connected to this has the highest freedom. The freedom of selecting the priority has to be given to the one who is connecting the device to the bus, right? Like a manufacturer, maybe, right? So Tata uses different priority compared to the maybe the Hyundai or something, I guess. Okay, so that's why the manufacturer uh, can decide the priority of messages sent by various nodes by using what is called as an identifier value of priority to that node or of that node. A specific node, you can assign the priority value, saying that okay, any message sent from this device should have highest priority, or any message sent from this particular device should have least priority. You can assign. Okay, right. Then there is another important feature. This is called as the CSMA. Right, we have two versions of that, either CA or CD. CSMA is the carrier sense multiple access. Okay, it's one of the advanced multiple access technique. We I think we have studied many multiple access techniques in the communication, right? Communication systems, right? Maybe TDMA, time division multiple access, frequency division multiple access, like that. We have a carrier sense multiple access. Okay, this is a technique used to avoid the collision avoidance. Just you, I want to, I know that multiple devices can start the communication simultaneously. But when that happens, there is a possibility that, right, everybody tries to send simultaneously, right? So, which means there is a possibility of messages getting collided with each other, right? And you lose the message sent by everyone. So to avoid that, we have a collision avoidance system, that is CA, right? CSMA is my major multiple access technique, carrier sense multiple access. Okay, first one is CA. You want to avoid the collision avoidance. Okay, so CSMA stands for carrier sense access. Carrier sense multiple access is the method that has been implemented here for multiple access system. Okay, provides the multiple access for nodes in the CAN system or nodes connected to the CAN bus. Okay, but when everybody tries to send, you have two things happening. One, either you lose a message, and second one is because of the collisions, right? Maybe, right, the messages will not reach the required destination properly, right? These are the two things. So how do you overcome that? There is what is called as a CA. So CA is collision, SION. A stands for avoiding or avoidance. Right. What this collision avoidance does is that it will check the bus status, and if it is free, then the node will transmit. Okay. So because of the implementation of CA, collision avoidance, right, you have to check the bus status. First, you check the bus status, and if you find that it is free, in the sense nobody else is communicating, then right, transmit the data. That's the first thing, right? Otherwise, you have to wait. Okay, so or you will wait until it becomes the idle. So there is another version that is called as CSMA CD, right? This is meant for the collision detection. So what do you want to detect the collision? In the sense, it would direct for the stopping of a communication if the data is corrupted, right? You already have sent a data, by mistake somebody else is also communicating, means, right, there will be a signal generated, right, on the CAN bus to all the devices who are communicating, who are actually sending the message, to stop the message, because, right, message has been mixed up, right, don't communicate further. Okay, so this is required uh, to just to direct to stop the transmission. transmission if the data gets corrupted, right? Specifically on the CAN bus, right? So that's the feature. Then we know that because of this CSMA CD, we have another feature coming up, that is the error detection. Okay, error detection is the next feature, right? Every CAN node has a self error diagnostic and the recovery state. So we will see that when we look at the data frames or the control frames, etc. Right? There is what is called as a error detection, self error detection, or it's called as a diagnostic and recovery state. There is a state given to each of the node, right? Just to identify that whether there is a problem, right? Whether the message is corrected, sorry, whether there is a message or the message is corrupted, or whether you want to correct. Okay, so every CAN node has a self error diagnostic state and recovery, right? So now you see, if the uh, node enters into what is called as the error diagnostic and recovery state, it has to send two types of messages. One is TEC, transmit error, right? That's a transmit error counter. And there is also one is REC, receive error counter. It is just to use to count the number of error bits received or error bits transmitted. Okay, it can use them, right? It can use the two counters, TEC and REC, so that, right, you can make the changes, like, right, what should happen on a bus, right? What should happen to the bus which is being used for communication, etc. There are many other possibilities which we'll see later. Okay, error detection is one of the features. Let's just remember that part. Okay, and then the last feature of that is that high speed and reduced noise. I try to club two things together. Now the maximum speed, right, is, I'll just write max speed of the CAN bus is 1 Mbps, which is too much for a communication between the devices inside the inside a vehicle. Okay, you will never be having GBs of data to be transmitted, right? Small information should be able to transmit it very quickly. So one, this is very much, okay. 1 Mbps is too much, right? And since you have a differential cable, okay, differential cable, so you always try to reduce the electromagnetic interference or no crosstalk. So no crosstalk and less electromagnetic interference. So these are the fundamental features of this thing. Okay, now I'll try to give a network architecture. Network architecture refers to how the networking view of, right, networking view of the protocols connection. Now you see, if you remember, there are several layers associated with the with a network, correct? If you remember, application, presentation, session, transport, network, data link, and physical, correct? The 7 layers of a network protocol, have you heard of somewhere? So you might have heard of 7 layers of protocol, correct? Communication protocol, namely application layer, presentation layer, session layer, transportation layer, network layer, then you have the data link layer followed by the physical layer. Physical layer is the physical media which carries the message. Okay. Now, if we go for the CAN, it's not like that. We don't have so many layers. That's actually another advantage of the CAN. Okay, so I never discussed about that so far, but it's actually very simple, right? The architecture of the CAN makes use of fundamentally only two layers. You don't have to have all the 7 layers over there. Only 2 layers are enough. Okay, so that is something like this. If let me assume that the communication happens between uh, two different ECUs. Let's assume. So I'll try to write the CAN architecture. And layers. So let me say I'm using the okay, this is ECU1 and this is ECU2. They are communicating, right? So the device has what is called as a control. Each device has a controller, something like a microcontroller. Then that controller gives actually has a part which is responsible for the CAN protocol. So that is a CAN controller. Each device has a main controller, which is a main computer, right? And it's going to have a CAN controller that is communicating with the CAN. I'll write transceiver, SEIVER. Okay, so this is device 1. So out of which there is a controller, there is a CAN controller and a CAN transceiver. You have bidirectional communication between them. Okay, now you see, okay, there is a ECU2 that also has another controller. Let me write like a controller itself. There is a main controller. This actually provides information or the commands to the CAN controller of that device. Then I'm going to have a transmitter receiver system, CAN transceiver. Okay, this is also what you have. So there is a bidirectional communication between the controller and the transceiver. Okay, so now what happens here is simply you have the wires. It's a twisted wire. You can twist and show as well. Okay, and you have a fixed value of resistance connected over here. Okay, so I'll write just 120 ohms on both sides. 120 ohms. So you see this gets connected to this gets connected to this. Similarly, this gets connected to this. It's connected to this part. So twisted wire. So I can call this is CAN L, CAN H. Now you see that I don't need 7 layers here, right? I just have a 2 layer. One is for CAN controller, one is for the actual controller, right? Both can be an application, right? Like an application layer which you have in the thing. But practically speaking, the data link layer which we have in the OSI layer is something like the CAN protocol. The whole protocol is controlled by the data link layer, equivalent to OSI model. If you consider that CAN protocol or the CAN controller is responsible, and it is equivalently, you can say that is a data link layer, which is from the top in OSI layer. That is the 6th layer. So all the 5 layers on the top are empty. You don't have to use them. No application layer, no presentation, no session, no transport, no network. You see, 5 layers can be omitted, right? Normal design of the protocol requires 7 layers, correct? But you see, that's why we said this is very easy to implement, right? You don't have to go for all those layers. Just design one data link layer, which is the 6th layer, and the last layer is a physical layer. So here physical layer is also, we can see there are two wires, that's all. Okay, so the if you want to look at the layers names here, so this is something like the, I just write DL layer. What is that? Data link layer. And this layer is a physical layer. So it is pretty easy and pretty simple to implement whenever you consider this to be uh, a protocol. Compared to the general protocols, this protocol has only two layers, whereas other OSI model or something will require seven layers. You have more things to design over there. Are you okay? So that's what is the first thing, right? Let's move on to the protocol itself now. So the protocol has different types of messages, right? And to control the message, you have to follow certain rules. So first, let's try to look at the CAN message, how a message looks like whenever a ECU generates and puts some message onto the, what you call as the CAN bus. Okay, so this is CAN messages, how the messages are going to look like. So, right, any device or any node that is connected to the CAN in the sense the CAN bus, it can broadcast four types of messages. Okay, so any node connected to the CAN bus can send four different types of messages. So what are the four messages? The first one is called as expected, this is the actual data. So data frame. What is a data frame? It's an actual frame which is used by a node for data transmission. Okay. Now, right, data frame. I'll just write the what is the meaning here. All right. So this is the data frame used by a node, right, representation of the actual data which it has to transmit. Then there is another type of the message that can be sent on a CAN bus. It is called as a remote frame, right? Any node can broadcast its information at any time or at certain periods or in a periodic fashion, right, on its bus. Okay, now something like the request for a data frame is called as a remote frame. You can request, any ECU can request a data frame from another ECU connected on, right? So that request will be called as a uh, remote frame. All right, request for a data frame is called as a remote frame. We'll look at this in detail, okay, later. Fine. Then not only that, there is another frame that represents the error. There is a possibility that whenever we try to send a message, it results in error. All right, so that is a third type of frame. It's called as the error frame. So in a CAN standard, if you send 5 consecutive bits of the same polarity, okay, that is right called as a bit stuffing concept. Actually, we'll see that later. All right, so it's a corrupted message. Okay, corrected message representation. And the fourth type of message that can be sent is called as a overload. It's called as a overload frame, right? Very similar to the error frame. Okay, it is transmitted by a node to buy some time, okay, if it is too busy, so that it can complete the pending task. If you want to see there is some time allocated, and within the time the transmission couldn't take place, and a node requires few extra time, okay, some time extra, so that it can finish the transmissions. For that, it can make a request. That is called as a overload frame. Okay, so overload frame, it's a request to buy more time to finish a task, right? These are the four fundamental message frames, right, that are possible, and any device connected to a CAN bus can send one of these four messages on the CAN bus. Okay, and the details of which message, what should be the format, what is the size, and what are the requirements, right, and with examples, right, what should be the data that we have to put. And so there are different fields present, like a register, like we have something called as the field allocated for control data, CRC data, acknowledgement, end of the data, etc. Many things we have, right? We have to see them in detail before we start writing a code for CAN protocol. Okay, so we'll be doing that in the next class.